The next speaker is Brian Miner from Washington State University, and the title of his talk is Data-Driven Activity Prediction Algorithms, Evaluation Methodology, and Applications. Okay, go ahead.
Good morning. So as you said, my name is Brian Miner, and today I'm going to talk to you about some of the activity prediction stuff we've been doing at Washington State University. So nowadays, with the Internet of Things and all of the different technologies we have, sensors are everywhere. We can observe almost any kind of human activity using sensors that we have available. And the problem is that we have all the sensor data, but what do we do with it? And so the goal that we're trying to work on is taking that sensor data and turning it into activity predictions that we can then use to make decisions in our applications. That's kind of what I'll be talking about today. So examples of some applications that we might want to use these predictions for include automating the home for energy efficiency, also for health applications for older adults. But there's really a lot of different applications that you could apply these to. And the focus of the work that I'm talking about today is mostly the step of taking the sensor data and turning it into predictions. And we do that using some time series and machine learning techniques. So this is an overview of what the activity prediction problem looks like. So basically, you have these sensor events that you collect that are coming in, and each event has a certain time, TE. And then you have these activities here, say eating, taking medicine, sleeping, and you want to predict the time from each event until that activity happens. So we're collecting these Y1, here is the time from the event to activity 1 starting, Y2, etc. And you collect those into your ground truth values, Y star. And then the goal here is to make an activity predictor that is able to form outputs Y hat that are as close as possible to those actual ground truth prediction times. So really briefly, kind of talking about activity recognition versus activity prediction. In activity recognition, the idea is that you look at sensor events you've already collected. And basically, you have these events, you don't know what activity is going on for those events. But what you do is you take an activity recognition method or have a human label them and basically split out your events and saying this activity happened during these events, this activity during these events. But with activity prediction, what we're looking at is actually trying to predict what activities are going to happen in the future and when they'll happen in the future. So you're looking at some time now, and you want to say how long until each of these activities starts. So that's kind of the contrast between activity recognition, which has been a lot more studied, and some of the activity prediction stuff that we're doing. So the problem set up here is we have our sensor data that we turn into feature vectors, which we're calling X. And then we take those feature vectors and combine them with our ground truth times, the Y star values. And we can label those sensor events using human annotators, activity recognition methods, different ways. But we basically combine those into our training data and use those to train a regression learner to form our actual activity predictions. And now the key insight that we had for the work that we're talking about is looking at the training data as an expert demonstrator, a way to view the training data as what we're trying to model and get our predictor to follow as closely as possible. So here, for example, you have different activities that you're predicting. And so each one of these has a different time at different points. You're saying this is how long until those activities will occur. At each point, you can take those outputs, those times, and make them into a multivariate output, Y star, and then combine those with your input features, and that forms your training data over a series of time. You just collect these up over time for your different events. And the goal here is to get the predictor to emulate those trajectories as much as possible. And so what we actually use is imitation learning, where basically the predictor is trying to learn the loss function, if you will, that the training data used, if you will, to generate those times in the first place. So we actually use two kinds of features. The first kind is what we're calling local features. Those are just features that are drawn from the sensor events themselves. They're things like time of day, location of the sensor events, how frequent are sensor events. But they're basically just information from the sensor events, and they don't necessarily relate the information about what activities are occurring in and of themselves. Then the second set of features that we use, and kind of the novel features here is the context features. Those are actually the previous predictions from the previous events, or lag values, if you will. And these actually bring in the activity context. So on top of just using the sensor event features, you're also adding this activity context. And when we do that, that's what we're calling the recurrent activity predictor. So we're also using what's called exact imitation learning. Basically, the idea here is that during training, those ground truth, or excuse me, the lag values, those context features, are taken directly from the ground truth values. But then during testing, we actually use the actual output predictions from the predictor for those values. And it's just a way of, again, having the predictor learn to imitate what the expert is doing in actual use. And we're also learning a multi-output regressor, where basically for each event, we're predicting all the activities simultaneously. And to do that, we actually just reduce it down to individual regressors for each activity. So each activity has, each activity has a regressor that is learning how to predict that particular activity. They all use the same features, but they're individually outputting their predictions, and then those are combined into a multivariate output. Now I want to briefly talk about evaluation. How do we evaluate our predictions and make sure that they're actually good? And a lot of it depends on the application and the context that you're trying to use. There's a lot of metrics in the literature, and oftentimes you want to use multiple metrics, maybe to get a better idea of the actual distribution of your errors or the different aspects of the problem that you're looking at. One metric that we introduce is the error threshold fraction. And basically this tells you, out of your total group of data points or errors that you're looking at, what fraction of them are below your threshold. And basically it gives you an idea of kind of how the error is distributed, what its characteristics are as far as the size of the error. So for our experimental results, what we did was we used 24 Casa smart home data sets. And basically these are, Casa smart homes are basically test beds where we have residents that live there, 1 or 2 residents. And they have sensors, as you can see here, that are placed throughout the home, different kinds of sensors. And basically we collect the data as the residents are living in their homes. And in this case, each of the test beds had up to 12 months of data, and we looked at 11 activities that people would normally perform every day, such as eating, cooking, sleeping, things like that. And so we actually looked at 3 different predictors here. So the first one is the independent predictor, which is basically the regression learner using only those local features drawn from the sensor events. So there's no real activity context that it's necessarily getting. Then we use the recurrent activity predictor, which again has both the local and the context features. And then finally, we looked at what we're calling the oracle predictor. And this predictor is basically the same as the recurrent predictor, except for instead of using the lagged values in your testing, you actually are using the ground truth values when you test. So in this case, using ground truth for both training and testing. The idea being that it kind of gives you an idea of if you can use some imitation learning techniques to correct from the all sorts of errors and learn how to correct from errors better through data aggregation, that's the kind of performance that the recurrent predictor might be able to achieve. And we also use the sliding window validation similar to a crossfold validation. So we looked at the mean absolute error, which is basically just the average of the absolute errors. And as you can see, the recurrent predictor has about half the amount of error overall as the independent predictor, which indicates that the activity context features really do help improve the performance. Then if you look at the oracle predictor, you can see that the performance improves even more, which hopefully would indicate that if you were able to use those error correction techniques and data set aggregation techniques, that you would be able to improve even further. So I want to briefly look at the predictions for each activity. So you can see that in basically all cases, the recurrent predictor has a lower error rate than the independent predictors. So for all the activities that we looked at. And then also for some of the activities, such as personal hygiene and relaxation here, the oracle predictor had actually almost no error. So again, that's a good sign that if we were able to use some of those techniques, we might actually be able to really improve performance even further. Now I want to look at the error threshold fraction. So for the independent predictor here, basically about 5% of the errors were below a second, whereas about 60% of them were below an hour. When you go up to the recurrent predictor, you see that about 16% of them are below a second, or 70 below an hour. And then when you look at the Oracle, it goes all the way up above 90%. So again, showing that as you add in this activity context and these refinements, you can actually get your errors to become smaller and smaller. A larger and larger fraction of them are small, which is a good sign. Also looking at it over the course of time, because again, we're basically training on so much data, and then as you move away from that training data further into time with new events that come in, how does the behavior change? So for the independent predictor, you can see it's quite volatile. It tends to jump around quite a bit, and a lot of that's due to the fact that there's no real smoothing going on. It only uses the features from each individual event, and so it's really subject to changes in those features. But then when we add in the recurrence, you see that it's smoothed out quite a bit more. It also tends to achieve a lower average error even as you get further away from the training data set. And again, even more improvements with the Oracle predictor. But the idea being that those recurrent features help to reduce the error as you go out further from your training set. Now we also set this up as a prompting app, kind of as a real-world application. So basically, we ran it on the iOS platform, and what would happen was the predictor would form predictions, and when an activity was predicted to occur, the user would get a prompt that looked like this, and they would basically respond whether they were going to do the activity at that point, they'd already done it, or they were planning to do it in the future. So we did a pilot study with 2 users over 2 weeks. And we got 112 responses from the users. They were pretty evenly distributed between the 3 options. Now, there was about 48 minutes of average error compared to when we detected activities using an activity recognizer. A lot of that we think might be due to the delay that happens with the iOS platform. There's some delays between when the server forms predictions and when they can actually get to the device itself, to the app. So that might be part of it. Basically, the predictions are stale by the time that they're actually delivered to the device, which is something we're trying to work on. But we also found that about 64% of the errors were below 30 minutes. And then if we looked at the error in our activity recognition, we actually see that that could be normalized up to about 72% of errors below 30 minutes. And an interesting thing here was that we found that the prompting actually influenced some of the users' activities. We had one user report that they got home from work and they were deciding whether to go out again to get groceries or stay home and relax. They got a prompt that said to leave home, so they decided to leave home and go out and get their groceries. So that's a good sign that, hopefully this can actually influence people's behavior, hopefully in positive ways. And it's a good start, if you will. So just kind of in summary, what we talked about today was data-driven activity prediction, trying, again, to predict activities from sensor observations. And our key insight was using the training data as an expert trajectory, we were trying to imitate. And then also using those context features from the leg values to help include some of the activity information. And then we demonstrated both test data and real-world use in the prompting app. And again, this whole activity prediction idea is kind of a big field, a big area. There's a lot of complexity, there's a lot of challenges that are still ahead, but we feel that this is a good step in the right direction in that field. And it's also a very important field that needs to be continued to be looked into. And with that, that's our website, and that's my email address, and any questions. Thank you.
Great. Any questions?
Yeah. Wonderful work. I was wondering whether we could use it to detect deviations from behavior, like anxiety or depression, and whether your prompts could push a person who is depressed into going out to the gym as opposed to vegetating in front of the TV.
Yeah, that's actually a good question. We actually had some people in our group that were asking about that when they found out that some of us were doing this. And that's something we'd like to look into. It certainly could be, because you could see if the person is predicted to do a certain activity or not. You might be able to kind of prompt them ahead of time to do the activity or otherwise adjust their behavior, hopefully. And a lot of what our group has looked at activity recognition, using activity recognition for generating prompts. When you say this activity has happened or hasn't happened, then we'll predict. But we're actually trying to look with this, hopefully being able to look ahead and start to do those prompting, not just in the moment, but also proactively prompt ahead of schedule as well.
Great. Any other question?
Thank you for the talk. Just asking about the model, because it's very reliable in the training data. So is your model adapted for, catering for new activities, maybe, if it comes?
At the current rate, we just train a certain. I think I understood your question as. Right now, we train a separate regression model for each activity, so there's no real, without retraining or adding. You could train a new regression, because it's split up into multiple regressors, so you could train a new one for a new activity, but they don't necessarily account for new activities in and of themselves. Yeah, I think that answers your question. Mm-hmm.
Okay.
I have a question, and your data, I think, obtain label is difficult. How do you obtain ground truth?
The ground truth?
Yeah.
So basically, we have those sensor events that we get that come in, and just have your sensor stream, if you will. And so sometimes we use human labelers, sometimes we use activity recognition algorithms, which are designed to actually perform labeling of the event, saying that this event is this activity. And the way that we do that with the activity recognition algorithms, they're trained on a model that's already been labeled previously with some event data that's already occurred from another sensor, or another smart home, or another, group of events. With the humans, it's kind of a matter of inference. The person will look at a visualizer and determine these sensor events are occurring in the kitchen, so they might be cooking. It's difficult to know exactly what the people were doing, and that's a lot of the challenge here is knowing what people are actually doing after the fact. And you can collect user feedback saying I was doing this at this point, but that's not always accurate necessarily, because users might not report what they were doing, or they might report it wrongly. There's a lot of questions in that that we're still wondering about, trying to figure out what's the best way to really predict those, understand what activities users were doing.
It seems the data is very noisy.
What's that?
It seems the data is very noisy because residents they may don't report their activity sometimes.
Yeah. So I'm sorry, it's hard to.
Okay,
with the echoing, it's a little hard.
I can talk to you later. And the second question is in your prediction, you use the regression for output regression. Why? My question is, have you ever compared it with NIOBS or HMM? Because in your experiments, you just show the result of the regression. You don't show the other results.
Yeah. So we haven't compared necessarily with a naive Bayes or a hidden Markov model or anything like that necessarily. We have compared it with, what we used for this talk was a model tree, which is basically a regression tree, but with linear models at each point, or each node. We have compared it in the past with linear regression or SVM, but we haven't looked at using any sort of naive Bayes based regression or anything like that. And you can't necessarily use like a classification method in and of itself that would just output a class label, since these are actual continuous values that you're trying to predict.
Okay, thank you. We may talk later.
Yeah.